Again, Calc AB, and welcome back. Sorry for the weird start here, but the iPad connection to the computer is a little wonky here at school. So wanted to make sure I got it working, and I'm not going to mess with it. So we're just going to jump right in. Basically, what we're doing today, guys, is we're learning another way to find volume of a solid revolution. Now, you might be thinking, well, gosh, we just had a couple of really nice methods with the disk method and the washer method. And that's true. Usually those would be just fine and get you through just about any situation. However, there might be an easier way depending on how the function looks that you're rotating, what the axis is that you're rotating around. And that's where the shell method comes in. So the idea is pretty simple. Okay, so much like with the washer method, right? When you were doing the washer method, you had a washer, okay, that had a hole in the middle, okay? And, that was actually a 3D sort of thick washer that you could see, okay? And the idea was that you want to find the volume of that. And, that's the classic, like how much dough is in the donut question, where you would go in, you would say, maybe you're going to, take the big volume and subtract out the little volume. And we knew we had a couple of radii in there. So we had this radius. If we imagine there's a center line going through, and the disk or washer method just basically says, look, when we revolve around an axis, if this is my axis of revolution here, I want to find the volume of this red disk. Well, I can see that there's a hole in the middle, so I find the big radius and find the volume of the entire disk. Okay, and we know the volume of a disk, right, is pi r squared h. Okay, and then we say, oh, well, I should make that a capital R, shouldn't I? Because that's our big radius. And then we have the other radius on the inside, the small radius of the small circle in here. And we said, oh, well, and then we have our little volume, which is pi little r squared h. And so the total volume of the red disk then is the difference of those two volumes. And so we'd say, okay, well, the volume here, pi big R squared h minus pi little r squared h. And since there's pi and h in both of them, we factored that out. And then we just got big R squared minus little r squared. And then we went on and said, okay, well, look, we know that the thickness, the height of this thing is actually some distance along the x-axis, right? So that turned into a dx. Oops, there we go. So we had pi big R squared minus little r squared delta x, and then we said, okay, now we're going to take infinitely many of these and add them all up. And that was what the video was that we had from the College Board. Now we say, well, okay, what if we thought about it differently? What if we said that shape is actually something a little bit different? It's thin cylindrical shells. Okay, so I want to first think about a single thin cylindrical shell. So think about like a ring, like a ring like you would wear on your hand, or a piece of hose or something like that. If you ever have seen the cement pipes that they use when your driveway goes across a ditch, if you live out in the country like Boston Harbor, you probably have what we call a culvert that goes underneath your driveway. Okay, and so in the case of that, what you have is you have this long pipe, okay, and it's hollow. And so if we were thinking about this pipe, and it should probably be straight and all that good stuff, what we want to think about is how do we find the volume of just the material that makes up the pipe? In other words, I've got this two radii situation again. Okay, so if I have my axis going down the middle of the pipe here, okay, then how do I talk about the two radii functions that are present? Okay, and so one way to do it would be to say, well, kind of similar to the washer method, right? Where we have a big radius going out to here, okay, and then we'd have a little radius going to here, and we would subtract them, and no problem, right? Okay, and that would work. We could take big R, find the volume of that outer tube if it were solid, and then we would find the volume of the hole through the middle and subtract them. And that works just fine. But it's not how we're actually going to go about finding them. And but let's before we get to that, let's think about this for a second. How would we find the volume of this whole thing? Well, we would need to know the area, and then we would need to know, the length of this pipe right here, right? And so that function right there is some kind of a height. Well, it's a length right now. Okay, so I'll call it L. So to find the volume of this thing, we could think of it like the old one and just say, well, look, let's figure out what does this big one look like, the big radius. Well, you'd have your, pi times your big radius squared. Okay, that'd be the area of that base times the length of the pipe. Okay, and then we would subtract out, okay, pi times the little radius squared, okay, times the length of the pipe. Okay, and that would work. But I'm gonna propose a different idea here. And it's going to be a little weird at first, but in the end, it's essentially doing the exact same thing. But we're going to define it all in terms of a single radius, and we're going to use the thickness of the shell as one of the parameters. So let me redraw this a little bit. Okay. And keeping the same idea, excuse me, the same general idea. Okay, if I draw my circle, my pipe like so, okay, and we have our pipe like this, and I have my inner container. Okay, I want to think about the average radius. Okay, so I'm going to turn this so it faces us. So we're looking at the end of the pipe. Okay, and so rather than do two different radii, okay, I'm going to describe a single radius called the average radius. And basically it's going to go from the center to halfway. Okay, we're going to call this the average radius. And we're going to use a Greek letter, a lowercase rho, okay, to indicate that we're using the average radius. Okay, and then we're also going to define the parameter here, the width of the shell. Okay, so if rho goes to halfway, okay, then the big radius is really just rho plus half the width. So I could substitute in there rho plus half the width. And by a similar logic then, the inner radius, the small radius, is really rho minus half the width. So we could substitute in there rho minus half the width. And here's what happens, okay? Through the miracle of algebra, we're going to get some pretty interesting stuff to shake out of this. Now, you obviously see the pi and the L that are in common. So let me get those out of there. So if I have rho plus the width over 2 quantity squared minus rho minus the width over 2, that quantity squared, if I square the two terms out, rho squared plus rho times w plus w squared over 4 minus rho squared minus rho times w plus w squared over 4. Sorry, I had to kind of squish that in there under my circles. Notice that there's a lot of canceling that happens here. Rho squared minus rho squared. W squared over 4 minus w squared over 4. But what we're left with is rho w minus negative rho w. So we get pi L times 2 rho w's. So the volume of the cylindrical shell here of just one shell is 2 pi, right? 2 times pi, you can see the 2 pi, times the average radius, times the width, times the length of our shell. That's the equation we want to think about when we start defining these thin cylindrical shells. 2 pi times the average radius times the width of the shell times the length of the shell, or when I turn it vertically, that'll be the height of the shell. Okay. Now, obviously, when we're talking about width, okay, just like when we had the width before, okay, what happened to the width was it went to 0. So that became like a distance on the x-axis that we turned into a delta x, which then when we put it in the integral became dx. Okay. And so this thin cylindrical shell becomes the basis for building our model for how we're going to do a solid of revolution. Let's go take a look at a better animation than anything I could possibly draw. Okay, so what I have here are some animated GIFs that are just going to kind of run, and I'll just kind of talk them through. And what I'd like you to look at is on the left-hand column, they're showing us then how if we take our shaded region, whatever we graphed in the XY plane, okay, and we consider drawing in that representative rectangle again. If you rotate that single rectangle around the axis of revolution, how it creates one of these shells like we just found the volume for. And so here on the left-hand side, you'll see a green rectangle get highlighted, and then notice how they revolve that green rectangle around the axis of revolution, which in this case looks like it's the y-axis. We'll just say it is the y-axis. And it makes a nice shell. Okay. And then in the second frame, in the middle here, what you'll see, if I spotlight that one here, okay, right here is they show you, okay, so now let's take each of those and revolve them around the axis. Now it does it halfway, so you can kind of see how the half shells are created, and then it's going to revolve them the rest of the way around. And so what you get a sense for is that, okay, so as an integral, then what are we doing? Well, we're simply going to add up all of these shells. Okay. Now there on the far right, you can see if we go to infinitely many shells, look what we end up with. We end up with this volume for this dish bowl looking thing. Okay, if I look at some of the other shapes, here's one where it looks like you know, they have a parabola that appears to be rotating around. Again, on the left side, you see the typical shell generation. Okay, in the middle, you'll see how they have multiple shells that get generated. And then on the far right, what would it look like if we had infinitely many shells? And they do that for a bunch of different types of functions that when they revolve them around this vertical axis. And the thing I want you to remember is that each one of those shells is generated by just revolving a rectangle around the axis of revolution. Okay, and so we can find the volume of one of those, and then in order to get infinitely many, well, we just let the width of those shells, okay, that width of that thin cylindrical shell go to 0 so that we have infinitely many. And that creates our integral. All right. Yeah, so this is a nice little animated GIF page here that just kind of shows with a bunch of different functions revolving around a vertical axis and creating what we call cylindrical shells. Okay. So back to our work here. If I take that idea and I say, well, let's do this. Let's define a function and let's see what it looks like when we revolve it around an axis like the y-axis, okay, a vertical line. Okay, so I'm going to take the intersection of two graphs. I'm going to have one of them be y equals x squared, okay, and the other one is going to be the square root of x. So let me start by drawing a quick little graph here of what this intersection might look like. And so when I graph y equals x squared, of course, it's going to go like through 1, 1, through 2, 1, 2, 3, 4, up like this. Okay, and square root of x is going to go like this. So x squared, y square root of x. And so you can see the region that we're going to be revolving. It's right here. I'm going to enlarge that region a little bit so that we can get a little better picture of it here. So here's y. Ooh, I didn't mean to do that. I'm going to draw my y equals x squared graph and my y equals square root of x graph. That's the point right there. And so when I draw in my representative rectangle, okay, wherever you want to draw that in is fine. Okay, that will generate a shell when I revolve it around the y-axis. So you can see it will revolve around and create some kind of a shell like so. Okay, where we're going to have some thickness there. And notice that the thickness right here is some distance along the x-axis. The length of the shell, okay, is the height of the shell, whatever you want to call it. Okay, we're going to want that in terms of x. Okay, the trickiest part here is the radius itself. Okay, how far is it for that average radius from the axis of revolution over to the shell partition? Okay, well, what do we call an arbitrary horizontal distance from the y-axis? Okay, we call that distance x. And what I find a lot of students have trouble with is defining that axis. In my classroom the other day, I talked with my students a lot about segment relationships, that for whatever reason, when you were in geometry, you learned pretty quickly that if you had a line segment and we knew the whole distance was 12, and we knew this distance up here was 3, could you solve for that missing distance? Sure, you could do that. Okay, this idea is going to play out a lot when we go to define rho. Not so much when we revolve around the y-axis, but when we move the axis of revolution away from the y-axis. That's the relationship that we're going to see play out a lot. So just a quick reminder that that segment relationship is going to be an important one. Well, if this is the way to generate a shell, let's talk about then how do we define all the different parameters. As I said in the previous part of this, we said if we want to find the volume of that shell, okay, well, it's 2 pi times the average radius function times the height function times the width function. Now, I'm making them all functions of x because now that I've oriented this the way that it is in the xy plane, I can see, oh, look, the average radius, how far is it from the axis of revolution to the rectangle? Oh, that's a function, that's x. Okay, how tall is this function? Okay, or how tall is this shell? Well, it's always top function minus bottom function. We can see that. Okay, what's the top function? That's the square root of x. What's the bottom function? That's x squared. So we know that the height function has the square root of x minus x squared. Finally, the width function. Well, you can see that the width of the shell is going to be some delta x. So it's a dx when we go to integrate. Now, last but not least, the limits of integration. The limits of integration are determined by the region that's graphed. Okay, so it doesn't matter what we do with the radius. Okay, I'm going to move the radius, or I'm sorry, not the radius, the axis of revolution. I'm going to move that in a minute here. But what I get for my limits of integration, those aren't going to change, no matter where you put that axis of revolution. Okay, the limits for this will always be the same. What are the limits? Well, where do the graphs meet? They meet here, that's at 0, 0. And they meet here, that's at 1, 1. So thinking about along the x-axis, with my innermost shell being in here and my outermost being way out here, the shells go from 0 to 1. So if this is the volume of a single shell, well, it looks like it says shill, hold on. Okay, the volume of the entire region then, the volume of this whole solid, we'll just add up all the shells. The integral from 0 to 1 of 2 pi times radius times height times width was delta x, but as we let it go to infinitely thin, it turns into dx. And that's how we'll find the volume for our solid of revolution using the shell method. Now, notice I would just go, well, actually, we take the 2 pi out, right? It's a constant. And so now I just have the integral from 0 to 1 of x to the 3/2 minus x cubed when I distribute my x in there. And voila, we have integrated. So we get 2/5 x to the 5/2 minus x to the 4th over 4 on the interval 0 to 1. Hey, the good news about 0 being one of our limits, right? Super easy to put in. Yeah, we're just going to get 2 pi times 2/5 minus 1/4. When we put in 1 minus 0, we put in that lower limit. I love having 0 be one of my limits. Okay, let's see, 2/5 and 1/4, probably going to be going to 20ths here. Sounds like it, huh? So let's see. Looks like we've got 8/20ths, right? Minus 5/20ths. So 3/20ths times 2 pi, or 3 pi over 10. And there we go. That would be the volume of that solid of revolution. Now, what if we were revolving around a different axis? Okay, what if we were revolving around, say, the line x equals 1, or x equals 2, or x equals -1, some other vertical axis of revolution? Okay, so take the same region and revolve about, let's say x equals 2, just because. No reason. Okay, I'm going to draw that out. Okay, so I'm going to say, well, look, okay, I know what my shaded region looks like. Okay, here's x squared. Here's square root of x. Okay, there's my region. We're going to pretend that they meet on this line here. There's 1. Okay, but I'm going to revolve it around the line x equals 2. Oh, well, that's way out here. We're revolving around this line here. Okay, now remember, I told you the limits will be determined by the region that we graphed at the beginning. Okay, this shaded region in here is the one that's getting revolved around the axis. Okay, it hasn't changed. I'll shade it in. And that's still, that shaded region is still bounded by x equals 0 and x equals 1. So that's not going to change. Okay, what is going to change is when I take a look at my representative rectangle and I think about the shell it's going to make now, which could be massive, right? It's going to go this way. Okay, and so, yeah, we're going to, oh, I was actually drawing the wrong thing there, wasn't I? So sorry. I meant to draw just the shell first. And so let's talk through all the same things. Has the height function changed? No, it has not. Okay, the height function is still top function minus bottom function. It's still right here. Okay, that's still h of x. That's still square root of x minus x squared. The limits are still going from 0 to 1. The width is still some small little distance on the x-axis. What has changed is the distance we have to go from our axis of revolution, which is here, over to the representative rectangle. Okay, how far over is this rectangle? This is where rho is now. So here we go. Practice those segment relationships, right? If the whole distance from the x-axis to our axis of revolution is 2. All right, guys, so here's where that segment relationship comes in that I was talking about earlier. We know the distance from the origin to the axis of revolution is 2. We know the distance from the axis, from the x-axis or the y-axis, excuse me, over to the rectangle is x. So what is this intervening distance right here? You got it. That's 2 minus x. That's what we're going to use for our average radius function. The radius from the axis of revolution here over to the representative rectangle, which is over here. Okay, that is what we get right here is our 2 minus x. So let's set the whole volume equation up. Our volume then is 2 pi. Now remember, the region has not changed. So the interval is still 0 to 1. Okay, the height function hasn't changed. The width function hasn't changed. What did change was our radius function. And so we end up with the integral from 0 to 1 of 2 minus x times the quantity root x minus x squared. And so you can see that by just adjusting where the axis of revolution is, changes the radius function, but nothing else in our integral. We can go on to integrate this. We will probably want to distribute. Okay, like we're going to get 2 root x minus x to the 3 halves. Okay, minus 2x squared plus x to the third dx when I multiply that all out. And now we're going to get, well, you know, this is going to be 2/3 x to the 3 halves times 2. So we're going to get 4/3 x to the 3 halves minus 2/5 x to the 5 halves. Okay. Minus 2/3 x to the third. Okay. Plus x to the 4th over 4. And now I evaluate that from 0 to 1. And that will give you the volume of this new solid revolution. When we put in the 1, of course, we just get 4/3 minus 2/5 minus 2/3 plus 1/4. Now the 4/3 minus 2/3 is 2/3. Oh, and this is whole, of course, minus 0. When we plug in that lower limit, there's a minus 0 on here, but of course we don't need to worry about that. So now we have 2/3 minus 2/5 plus 1/4. You know, the common denominator for 3, 5, and 4, unfortunately, is going to be 60. And so you know, this is 40/60 minus 30/60, which is 10/60 plus 15/60. So now we get 25/60 times 2 pi, or we get 25 pi over 30. And that's our volume for this solid revolution. So as you can see, when you are using the shell method, okay, it's nice because we only have one radius to worry about. We do have this height function we need to worry about, the height of the rectangle. Now, why would you use this method? Okay, the last little bit here before I sign off, and you may have noticed my background change. I gave up trying to make this video at school. I've started and stopped it so many times today, it's been ridiculous. So hopefully we can finish it up here at home where I have much more stable internet. So why would we do this? Why use the shell method? Well, I want to take a look at what the disc or washer method would have done with my original problem here. You see, if I had taken that same region that we're talking about here,
and said, okay, we're going to revolve that around the y-axis. Oops. Let's draw that a little neater. Okay, we're going to get this kind of weird looking bowl shape thing. Notice now my discs would be horizontal, like so. And so I'm going to have to rewrite my functions so that they are all with respect to y, because now the thickness of my washer is delta y. And that's where I find first year students sometimes prefer to have the shell method handy, because I don't like rewriting things in terms of y. I don't like integrating with respect to y. I've been doing dx for a long time, so it makes sense to be able to keep things dx. This one isn't particularly complex, okay? Because, you know, if you have x squared equals y, then you have x equals the square root of y, okay, for your outside radius. And if you have square root of x equals y for your inside function, then you have x squared equals y for the small radius. And so you can just put those in on here. So you can see like the outer radius right here to this function. Well, that's y equals x squared. That's also x equals square root of y. So now we have big radius, little radius inside here. Okay, that's x squared. Okay, but if I don't have to rewrite it, I can keep the rectangle perpendicular to the x-axis. That means I'm integrating with respect to x. It's especially handy if you have something like this revolved around the y-axis, bounded also by x equals 0 and x equals 1. Because in this case, if I have y equals x squared like this, and let's go out here, and this is 1. Notice if I'm revolving around the y-axis again, the shape is actually two different solids. Okay, there's a solid cylinder at the bottom, and then there's this bowl at the top. So if I'm working horizontally, like I'm drawing this disc in here now, I actually have two integrals. I have the integral from 0 to 1 and the integral from 1 to 2. Okay, which, okay, not the end of the world. But if I go with my representative rectangle being a vertical rectangle, like I'm setting up for the shell method, then it's only one integral. I'm just integrating from 0 to 1. My shells then are going to look like this. And you can see that the volume would be 2 pi integral 0 to 1. Average radius function here is just going to be x. Height function is just going to be x squared plus 1 dx. And that, I think, makes life a lot easier when you're integrating. And I can see my screen didn't catch up. Sorry, guys, I took a minute for the video to catch up there, the iPad, but here it is, the volume that I would use that for. So that's a little bit about why. So in general, then, what I like to think of is if my axis of revolution is a vertical line, okay, like this, then I think you probably want to consider the shell method. I do believe that that will save you some time. You won't have to do the rewriting, and you'll be integrating with respect to x. If the axis of revolution is a horizontal line, then by all means, stick with the disk and or washer method that we learned yesterday, because that will also keep you integrating with respect to x. You won't have to rewrite everything in terms of y. Now, there's going to be some times when the functions won't lend themselves to that rule, and we'll talk about those in class. But I think as long as you stick to that general rule, I think you're going to find that you'll be able to figure them out a little easier. So in general, if the axis of revolution is a horizontal line, use disk/washer method. Okay. If the axis of revolution is a vertical line, use the shell method. And that will always keep you integrating with respect to X, and your representative rectangle will always be a vertical rectangle. All right, guys. Well, I have been trying to make this video all day. It is now 5:12 p.m. here, and I think I'll be able to edit this all together into one cohesive video, I hope. Anyway, thanks for hanging with me, guys. It's been my pleasure to make this video for you. Ms. Hoagie's class, I'm sure she'll have some other examples for you that will be by far more beautiful and well drawn than mine are on this iPad. All right. Thank you so much, guys. Have a great day.